We're now going to do another example of changing the order of integration. So a problem is to take the integral where x goes from 0 to 1, y goes from the square root of x to 1, and z goes from 0 to 1 minus y, and rewrite it so that we first integrate over x, and then integrate over y, and finally integrate over z. Now this is a little bit tricky, but we can do this if we think through it logically step by step. So I'll show you how to do that. The first thing we have to do is write down the integration region. So any iterated integral like this is a triple integral over some region, and the limits of integration give us inequalities which define the region. So in the outermost integral, we're going from 0 to 1, so that means that x is between 0 and 1. And in the middle integral, it tells us that y is going from the square root of x to 1. So I have the square root of x is less than or equal to y is less than or equal to 1. And in the innermost integral, the limits are 0 and 1 minus y, so that tells us that z is between 0 and 1 minus y. So the region over which we're integrating is defined by these 6 inequalities. Now, to simplify the discussion a little bit, we can notice that a couple of these inequalities are redundant, so we can cross them out. So, first of all, it says here that x is less than or equal to 1, but the inequality below it tells us that the square root of x is less than or equal to something, which is less than or equal to 1. So the square root of x is less than or equal to 1, and that implies that x is less than or equal to 1. So this inequality, saying that x is less than or equal to 1, is redundant. It follows from the line below, so I'll just cross it out. Also, this inequality here that says that y is less than or equal to 1 is redundant, because in the line below, we see that 0 is less than or equal to 1 minus y, which is the same thing as saying that y is less than or equal to 1. So I can cross this one out too. So now I have 4 inequalities defining my region. Now let's draw a picture of the region. This is actually not necessary to solve the problem. We can solve the problem purely by logically reasoning through the inequalities. But I'll draw the picture anyway just to help illustrate what's going on. So first of all, what is the boundary of this region? So the boundary of this region consists of various surfaces. And these surfaces are given by setting any of these inequalities to be an equality. So the boundary surfaces are where 0 is equal to x, square root of x is equal to y, 0 is equal to z, and z is equal to 1 minus y. So now we can sketch these to get a look at the region. Now the surface x equals 0 is just the yz plane. I won't draw that. The surface square root of x equals y, well, that's x equals y squared. So I take this parabola, x equals y squared, in the xy plane, and then that extends up. Z equals 0 is the xy plane. I won't draw it. And z equals 1 minus y is this line in the yz plane, and then extended in the x direction. So now I can connect these like this to get a sketch of my region. So this front surface here is the surface square root of x equals y. This upper surface here is the plane z equals 1 minus y. In the back, I have the plane x equals 0, and at the bottom, I have the plane z equals 0. So that's my region. All right, now back to the integral. So let's rewrite the integral in the order we want. So first I want the z limits. So I need to think, if I don't know anything, what is the smallest and largest possible value of z? So I have to look at all inequalities that involve z. Now the only inequality saying that z is greater than or equal to something is this one. It says z is greater than or equal to 0. So the lower limit of z is 0. Now what about the upper limit of z? Well, z is less than or equal to 1 minus y. Now the problem is we don't know yet what is y. So I want to say what is the biggest that z can be, and that's equivalent here to saying what is the smallest that y can be. And if you look at the other inequalities, what they tell us is that y is greater than or equal to 0. So the smallest that y can be is 0, so the biggest that 1 minus y can be is 1, so the upper limit of z is 1. Now, for the next integral, we have to say, if z is fixed, then what are the possible values of y? Now, the inequality here tells us that y is greater than or equal to the square root of x. We don't know what the square root of x is, but we do know that it's greater than or equal to 0. So y is greater than or equal to 0. Well, this inequality, if we rewrite it, it tells us that y is less than or equal to 1 minus z. So the largest possible value of y is 1 minus z. And then for the innermost integral, we have to say, if z and y are fixed, then what is the range of x? So we have to look at inequalities involving x. The first one says that x is greater than or equal to 0. And the second one says that the square root of x is less than or equal to y, which is equivalent to saying that x is less than or equal to y squared. So x goes up to y squared. Then I have f dx dy dz. So you just logically reason through this. For the outermost integral, you just say, if you don't know anything, what is the range of the outermost variable? And then for the middle integral, you say, well, if the outermost variable is fixed, then what is the possible range of the middle variable? And then for the innermost integral, you say, if the outer two variables are fixed, then what is the range of the innermost variable? And we can also see what's going on from the picture. So we could look at the shadow of this region in the YZ plane. So that's a triangle like this, where this is the line z equals 1 minus y. So z is going from 0 to 1. For a given z, y goes from 0 to 1 minus z. So that's this line here. So y is going from 0 to 1 minus z. And then the innermost integral tells us that for a given y and z, x is going from 0 to y squared. So we can see that in the picture here. So it starts at the back where x equals 0 and comes to the front where x equals y squared.